see any of you were here for that. Almost 2 months ago? I think I went like the whole 55 minutes. But there is a seminar after this at 4, I believe. All right, or is it at 5? And then the reception's at 5? Okay, so I'm going to try to get done by then. I should be short enough. But I guess I'll go ahead and get started. I don't know if anybody else is going to be here. So, are you ready? Are you getting a good?
Ready if you're ready.
Okay, I'm ready. Yeah, thanks everybody for coming. If you guys don't know me, my name is Professor Prather. I'm giving a talk on the quote-unquote rebound pendulum. I don't know that this is at all a canonical term. I was solving a problem from dynamics, as I've been teaching it for a couple semesters now. And there was one problem that kind of stood out to me. I would say maybe it's my favorite problem from the class. But what I did in this talk is I try to solve it in a way that I think is a little unique, the way you might solve it in class. And it involves energy dissipation. So the reason I'm looking at this rebound pendulum, I wish I had time to bring or build a demonstration to show you all. But let me start with a little bit of background. So ignore the abstract. I'm just going to start with a problem statement. We'll look at how I can motivate the problem. I'll discuss some assumptions that I have to make in order to solve it the way I want to. I'll go through how I solve it, how it relates to this thing called the coefficient of restitution, or the restitution coefficient, to say it shorter. Then I'll identify some relationships between that and some of the parameters we can measure. I'll discuss energy losses and how we can get practical measurements of them, and then I'll compare it to some other analogies. So this is the problem statement. As you might notice, it looks just like a textbook problem. We've got this pendulum here that has a 15 kilogram solid ball attached to the end of a 6 kilogram rod. But my argument will be that I don't care what mass ball or rod I have. That's one of those things I don't really care about. They gave it to me, but yeah, whatever. So they say if we release this pendulum from 90 degrees, so theta is measured vertically from here. So at 90 degrees, the pendulum's up at 90 horizontally, sitting like this, and we'll let it go. Have you ever seen a Newton's cradle before? Right, you can kind of imagine what's going to happen. This thing is going to swing down, it's going to hit the wall, and it's going to bounce back up to some other angle. The idea here, and specifically in this chapter in dynamics, it's about impulse and momentum. So some energy is going to be lost. We don't really know how much or where. The idea is we're trying to figure out what is the rebound angle, theta 2, after this thing hits the wall and bounces back up to some new angle. I think you could all imagine that if it were 100% energy efficient, it would bounce all the way back up to 90. If it was completely energy inefficient, all that energy would be absorbed and it just sits there stuck to the wall like it was somehow glue or some kind of clay or something. It just kind of falls and it just stops. But in this problem statement, we have these assumptions and it says, okay, find this rebound angle theta 2 if the coefficient of restitution E is 0.6. So let me motivate the problem before we jump into it. So how can we measure or calculate the energy from a single collision? This is an idealized case. So I'm going to drop some assumptions, several assumptions. But how can this rebound angle, this rebound height, and its velocity relate to the loss of energy? You might have some ideas as to why. You know how you can relate height to potential energy and velocity to kinetic energy. But another question I might ask is, how does this rebound angle relate to the coefficient of restitution, this 0.6 that they gave me in the problem statement? And then how does that relate to energy or efficiency? And maybe the more important question is, why is this even interesting to begin with? Or is it useful? Well, to continue motivating this with a little bit of history, I guess in 1602, Galileo was the first one to really discover the isochronism of a pendulum, saying that it's independent of its amplitudes, with the exception that it's only for small angles. This is not an exception I will make today, but the idea was that you could use pendulums for timekeeping, And in 1656, Christian Huygens built the first pendulum clock based on this principle of pendular motion. He was the first one to kind of describe this mathematical treatment of oscillatory motion. And then two names that I didn't know of until maybe a couple hours ago are Benjamin Robbins, who invented the first ballistic pendulum, which if you've taken physics 1 here, you've done an experiment with a ballistic pendulum. It relates momentum and energy together. And then, 1901, I'll probably mess up the first name, George S. Charpy. Anybody correct me if I'm wrong, but he invented this thing called the Charpy impact test, which is still used to this day to measure fractures or energy that's absorbed by a fracturing system. So, what assumptions do I need to make to solve this problem? Well, I mentioned earlier, we'll assume that this starts at an angle of 90. And that's fine, but I still have some other things I need to assess before I can just wave my hands around and solve it. I have to assume that it collides perfectly. And what I mean by perfectly is that, if I go back to the picture, that spherical ball must collide perfectly, one more time, with the wall. You might have noticed I made an adjustment right here. You might not have noticed that. Hopefully you didn't. But the radius of this ball is 300 millimeters. And so as this pendulum slides down to theta is 0, this radius should equal the distance of separation from the wall. Otherwise, it's not a perfectly perpendicular collision. It would be at least against the sphere, but not perpendicular to the rod. So, with that assumption that it strikes perfectly perpendicular, I got a couple other ones here. Let me get back here. I'll also assume that the rebound surface is fixed. Right? If it's not fixed, it could move, and that would change how the energy is transferred. So I'll say it's fixed and remains stationary. And I'll also say that the pendulum's moment of inertia remains constant. It's not going to change. We don't have any deformations. I think in the real world, right, you would have this thing hit the wall, and maybe it would bend. Maybe there'd be a dent in the wall. So I'm assuming that there's no deformations at all, which is quite an assumption, quite an idealization, but this also relates to the fact that energy will be conserved leading up to and immediately following the collision, but not during. Some energy is lost during the impact. But what I'm going to do for now is ignore any friction along the axle, right, of this pendulum. It could be a string, if you think about a Newton's cradle being pretty frictionless. But I'd also have to ignore drag forces, because this thing has some surface area as it moves through a fluid, aka air. And the last one is that, as I kind of already mentioned, energy is lost during the collision. This is what we call an inelastic collision. It's not elastic, energy is not conserved during the collision, and it's not a plastic collision where energy is completely absorbed, so it's kind of in between. All right. So in terms of working the problem, I was going to write this all up on the board, but I think it'll be quicker if I just point my fingers to what I'm going to say. So, consider the energy before and after the collision. I mentioned as the assumption, right? Energy is conserved leading up to and immediately following the collision. So I've done this in 2 phases. On the left-hand side is the energy before the collision. So you have this thing raised up to some height, theta is 90 degrees. You got some potential energy. I let go of it, converts that energy into kinetic energy, which I've called 1 final, where 1 initial is the initial stage. So anybody who's in my class knows I'm weird with subscripts. I try to be as explicit as I can. But in the second phase, after the collision, I have some kinetic energy, right, bouncing off of the wall. And that energy is exchanged for the moving of the pendulum up to some new height, h2. So I've taken these 2 phases with energies, and you can relate them together, and the idea is, well, somehow this coefficient of restitution has something to do with the energy loss. You might notice there's nothing to do with that coefficient here, it's E. But my little trick in this problem is the claim that the moment of inertia must remain constant. I guess in the real world it might change, it might deform, but if I say, by assumption, the moment of inertia of this system remains constant, then I can leverage that and put them together and say that they're equal to each other. So, if it remains constant throughout the collision, I can relate the moments of inertia I, and you'll notice the mass term cancels out, along with G. G is also constant throughout this whole behavior. And that 2 that's just kind of hanging out over there. So after we make this relationship, I can say, well, the final height, h2, the proportion of the final height to the initial height is also related to its output speed over its input speed. And I know this says F down there, don't get confused. This is the final of the first phase. This is the initial of the second phase. So this is the velocity as it leaves. This is the velocity right before it collides. So anybody have any questions on any of that? Just making sure everybody's with me. I know I'm just doing math right now. But the idea is that I've just related the moment of inertia to just get a nice clean proportion between the heights and the speeds. But you might notice that those heights remain in the first order, whereas I square these velocities. If you know anything about energy, you might have some inclination of where that might go. But, okay, great. So I found the rebound height, h2f. I can at least relate it. But this equation still really has 2 unknowns, right? h2 of f, what's the final height, and what's the final speed? I haven't even answered what the heck the angle is going to be. So, let's keep going. So dynamics, we're talking about this thing called the restitution coefficient. And I won't go through this whole picture, but the idea is that we can relate the ratio of the deformation impulse to the restoration impulse. So when 2 masses come together, they collide, assuming VA is faster than VB. They deform. There's this little deformation that happens. They reach a maximum speed moving together, and then they restore themselves to some final speed. You can imagine throwing 2 tennis balls at each other. You know, they're going to compress maybe for an instant. They'll move together before they rebound back to their initial state. The speed at which they move after the restoration depends on this impulse, this ratio of the restitution impulse to the deformation impulse. And you can relate that through some math to get this ratio of speeds. We have VB2. If you imagine A and B are the 2 particles, VB2 minus VA2 over VA1 minus VB1. So you take the after velocities divided by the initial velocities. Again, kind of a before and after type thing. But if I permit that, well, I'm jumping ahead a little bit. I mentioned elastic, inelastic, and plastic. So if all the energy is conserved, this coefficient is 1. If all the energy is absorbed, this is 0, but we're looking somewhere in between there, with E being 0.6 in this particular problem. So, as I was about to say, if we assume that the rebound surface is fixed and doesn't move, then the velocity must be 0. It's not going anywhere. Which is nice because it cleans up my expression quite a bit. This coefficient, this restitution coefficient, VB2 and VB1 are gone. I'm left with a nice little ratio of velocities. But you might notice there's a negative sign there because it usually exchanges directions. But in this case, VA1 is moving to the left initially, and then VA2 is moving to the right. So if I've got a negative VA2 over a negative VA1, I end up getting a positive coefficient. But with that ratio of speeds, it kind of prompted me to think, well, earlier we had this relationship of heights and speeds. So what if I just square that coefficient? Then I can say that the output speed squared of the input speed squared is this coefficient squared. Right? So just taking this, squaring it, plopping it in right there and saying, well, that's just E squared. Everybody following? Anybody have any questions? I've still not answered the angle. Right? We're trying to figure out what's the angle of rebound. Promise I'm not leading you astray. So continuing, if I use a little bit of trig, and I'll just draw a picture, I suppose. If I take my pendulum here, swings down to here, and then maybe it reaches a rebound height somewhere over here. All this whole length here, the initial height. I've kind of messed that up a little bit already, but we'll call this the final height. I get this triangle right here. Oh, which one do I want to do? I get a triangle where this is my final height minus initial height. This is the initial height itself, which is the length of the pendulum. And this is my angle theta. So if I do a little cosine with the adjacent hypotenuse, I'm sorry, h of I minus h of f. Over the initial height, I get this 1 minus h of f over h of I, which might seem a little interesting because I've got an expression for h of I, or h of f over h of I, e squared. So without going too much further on the board, I'll just redirect this back over here. If you make this relationship, you get 1 minus the output height over the input height. And then rearranging some stuff and plugging it back in, as I was saying, you can relate this all back to this coefficient of restitution squared. So if I rearrange that to finally solve for the angle, theta 2, the rebound angle, is the inverse cosine or arc cosine of 1 minus e squared. I don't care about the mass, I don't care about the speed, I don't care about the height. All you have to tell me is what is the coefficient of restitution, and I'll tell you the rebound angle. So in that problem statement, yeah, they give me a whole bunch of fun stuff. The mass was what? Like 12 kilograms or something like that for the ball. Let me get back up here real quick. 15 kilogram solid ball, 6 kilogram rod. But if you type this into your calculator, the answer to this question is 50.2 degrees. If you take the inverse cosine of 1 minus 0.6 squared, you will get 50.2 degrees. And to me, that is a fairly elegant solution. But that's not all I have in store for us. Let me catch back up real quick. Make sure I don't go too quick. Okay, so we just got the angle. But wait, there's more. So I want to identify some relationships. I kind of mentioned this subtly earlier, but you might relate this height to the potential energy. They're proportional to each other. And the kinetic energy is also proportional to the velocity squared, whether it be the translational velocity or the angular velocity, whichever one you like more or whatever one is easier for you to measure, perhaps. But if I could relate these in terms of ratios of energy, then I can say that the efficiency, the energy loss, or the amount of energy that I retain, I should say, the percentage of it, can be related to this ratio. So E, epsilon, can be related to E, the coefficient of restitution. If I square this, I get the efficiency. And I thought that was pretty compelling too, because, okay, I can take this coefficient of restitution, yeah, it's something that's just measured, like an index of refraction. Just a kind of a material type property of the interaction between those two things. So all I got to do is square it, and I get the efficiency of the system. I can take cosine of the inverse cosine of 1 minus that value, and I can find the angle of the rebound. So yeah, that's kind of cool, I guess. But if I put all of that together, and then say, what if cosine of theta 2, moving some stuff around, gives me 1 minus e squared, or 1 minus the efficiency? Well, 1 minus the efficiency is the inefficiency. So kind of connecting all the dots I could possibly imagine. Anybody seen That's Always Sunny in Philadelphia with the Pepe Silva? And it's like, I'm always just pointing, yeah, that's how I feel. But I'm trying to connect all these things together, right? So if you take this other parameter, inefficiency, let's call it chi, then I can just relate all of this together in a kind of cool way. So yeah, I don't know. I kind of went down this rabbit hole with the dynamics problem that, yeah, okay, I found the angle. That's all good and well, but what else can I do with it? So let's see. So just kind of recapping a little bit with this particular problem. We've shown that we can relate this coefficient of restitution to energy and efficiency. And if you'd imagine, as I mentioned earlier, an elastic collision where energy is conserved, well, the heights would be equal to each other. So would the rebound angle be equal to the inbound height. With a plastic deformation, all that energy is absorbed. It's like if I were to drop this into like a thing of mud and it just sticks there, right? But we're looking at an inelastic collision, kind of in between. One thing that I also noticed, I thought this was kind of weird. in the extreme cases, elastic and plastic, well, 1 squared is 1. 0 squared is 0. So they don't really have any differentiable features until we're in the inelastic stage. So why is it E and not E squared or any of that stuff? I kind of thought that was interesting. But how can we measure this? Because I can throw a theory around all day, but it doesn't really make a difference until I can measure it. So we're talking about inelastic collisions. If I were to properly write the conservation of energy, I would include the non-conservative work that's done or taken out by whatever these things might be, whether it's heat, friction, drag, sound, or any deformations that I ignored earlier. But in kinematics, we usually ignore these and are pretty safe to do so, for the most part. And I would argue, I put a question mark at the end because I don't know that this is a true question or a true claim. I think it's kind of hard to measure energy losses. Maybe somebody would agree or disagree, I don't know. But it seems like a pretty decent challenge. Now, I can measure velocity. I can measure mass, I can measure distance, I can measure time. But how do I measure energy loss? Well, consider that gravity is a conservative force, so the path that it takes doesn't, the work that's done doesn't depend on the path. So differences in height aren't going to be due to a loss of gravity. They're going to be due to a loss of some other type of energy. So what I could do is figure out a way to measure the drag forces. We know that they depend on the velocity. There's 2 different types of drag forces really in kind of general. You have the drag force for quote unquote large objects, really just objects that are not well defined by a circle or a sphere. So take the drag force, 1 over this coefficient of drag, the density of the fluid which it moves through, its cross-sectional area, its velocity squared, the distance over which it moves, and I threw cosine of theta in there just to generalize in case the force doesn't move in the same direction as displacement. Did the same thing for Stokes' law for small objects, where instead of using a cross-sectional area A and some coefficient of drag, we just use the 6 pi r, and then eta is the viscosity of the fluid, and v is the velocity. So, in theory, we could measure the velocity, right? I could take, anybody ever watch Mythbusters? They've got the little slow motion cameras, put a little grid behind it, and I could figure out the velocity of this thing as it collides up against the wall. I could probably measure friction to an extent. It might be hard, but it might be able to be done. I don't know. I'd have to get a really good representation of that axle, figure out how exactly that friction's transferred, how it rotates, slides along the surface. But there's other forms of energy that could also contribute to energy loss. One of those is sound. All right, these pendulums make sounds when those Newton's cradles, they click clack, right? I can't imagine there's a whole lot of energy that's lost to sound, but I could probably measure it. I could take the, trying to remember the exact word, I just looked it up, the sound pressure level, P squared, divided by the density of the air that in which it moves through, the speed of sound in air. This is the surface area of a hemisphere, and then I could figure out how long that sound took to propagate. So I could actually measure the sound. I should be able to measure the heat. That's just your standard heat equation. You might be thinking, well, is there really that much heat that's generated? I don't know. Maybe. There's a joke that if I slap the chicken like 30,000 times a second, I could cook it. So technically, if I were to collide this pendulum together, I should produce some measurable amount of heat. It might not be easy to measure, but it might be measurable if I have a precise enough set of instruments. The last one that I thought of, just trying to think of all the things that could contribute to non-conservative work, I also thought light. Because I was watching, anybody ever heard of the slow-mo guys on YouTube? They had a video of these bullets going through glass. And before, I'm trying to remember exactly what part of the collision it is, but there's actually just a brief flash of light. It's not from the shell igniting. There's actually just this brief flash of light. And I thought, well, I'd probably have to have this pendulum moving pretty quick for it to generate anything like that. So I just considered it to be negligible. But the idea is that there's some energy that's lost to drag, to friction, to heat, to sound, and maybe even to light. So I should be able to measure all those things. And if I know the coefficient of restitution, or maybe I could even measure it, then I could do a kind of energy audit and say, hey, okay, well, this is how much energy is supposed to be left in the system. how much energy can I measure that has left? And I could figure out if they agree or not. So I said, well, so what are some of the practical measurements of energy loss? I've kind of mentioned these already, but energy loss to drag, right? I can measure the inbound and outbound velocities, just like they do on Mythbusters. I could even measure the angular velocity by putting a little radial gauge on there and just measure that in time. But if I know the speed, I could estimate the drag force. I'd have to average the velocity because it goes from 0 to its maximum from either stage. But I could also find the energy loss to sound, as I mentioned before, acoustic energy losses, or thermal energy losses, and just kind of see how those compare and stack up to get this total energy in the system. So I've got a few more analogies before I wrap up. The first one I call the trivial analogy. If you take this mass over here at some height and I drop it, if any of you has ever played basketball, you know what dribbling is. And in my understanding, dribbling is the act of inducing more energy into the system so that it returns to its original height. So, drop this thing without any dribbling involved. Well, it's not going to reach back to the same height that it started with. If you do a little bit of the same procedure that I did before, you'll find that the coefficient of restitution is as we've seen before. So it works just in a nice simple case where something's being dropped from a particular height and rebounds to another height. It works for a pendulum as well. This is also true in fluid mechanics. So if you take this tank, I've got a orifice here where water's flowing out. If you take fluid mechanics with me, we'll do this lab. It's 106. Where basically we measure this thing called the vena contracta. There's a certain relationship between the head loss and the velocity as it flows through this orifice. But if you look here in figure 3, there's some head loss due to the constrictions. So based on the geometry, which is kind of my argument that it all has to do with geometry, there's a kind of a hard corner there. They start to smooth out here, and then even less, well, more smooth, but less energy loss there. So we measure this energy based on the velocity as it flows out of this vena contracta. And if you go through the whole Bernoulli equation, blah, 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 you end up with this thing called the coefficient of velocity, which, believe it or not, looks just like the thing that I said is the coefficient of restitution. Thought that was kind of neat. But yeah, so I don't know. I found that to be fairly compelling, so I called that the insightful analogy. I've got one more, and it's the invalid analogy. You'll see why I consider it not to be valid. So if you consider pushing a block along a surface, right, this is work equals force times distance times the cosine angle between them. If you're not using the vector, you're using the scalar form. But if I push this thing purely horizontally, right, all of the force will contribute to motion. But if I incline that force at some angle, only the horizontal component of that force produces the work. Okay? If I put that force vertically, say theta is 90, well, I would never get any work done because I would just be wasting that force for however long I applied it. But if I apply it at 45 degrees, I think we could all probably agree that's right there in the middle, right? Halfway between 0 and 90. I thought, okay, what if I blindly apply this analogy to this situation? Okay, so take cosine of 45. Take 1 minus that value and you get 0.293. That is not 0.5. Like, wait, what's up with that? Well, what got me thinking about this is I actually gave this as a problem on my General Physics 1 exam. And I asked them what the efficiency was. And I just kind of thought it has to do something with the cosine of theta. But I didn't really go down the rabbit hole as far as I should have before I assigned that problem. Because, as somebody asked me after the test, I was like, well, I think you're supposed to square it. Because I know cosine of 45 square root of 2 over 2. I was like, well, I'll just take this and square it. If you take that and square it, you get 0.5. So in this weird analogy, this is why it's not valid with this set of circumstances, is that here the efficiency is just strictly the cosine squared of theta. It has nothing to do with 1 minus, or there's no square. There is a square here, unlike there was before. So I don't know. I thought this was kind of interesting. Of course, it breaks my analogy that I've been building. But I thought this was interesting because there are different applications, and you can't just say, I've got the analogy, I've got the solution for everything, let's just apply it everywhere. Because in certain cases, it breaks down. and this is one of them. So in conclusion, as we've demonstrated, right, we can develop this chain of relationships between the coefficient of restitution, the efficiency, the inefficiency, the cosine of the rebound angle, the heights, the speeds, and all that. And this is basically the bridge between theory and measurement. So I propose there are 3, maybe 4, ways to measure the efficiency or inefficiency. You can measure the height, you can measure the angle, and you can measure the speed. And I say 4 because technically there's 2 different speeds. So I could measure the angular speed and the linear speed and compare those 2, but you might argue that's redundant. I don't know. But the other one is that I have 3 not so simple ways to measure the energy loss, right, in terms of heat, sound, and drag forces. But I've got a couple future work ideas here. Like I mentioned earlier, this coefficient of restitution is a material property. At least it's not a material itself, it's the interaction of 2 different materials together. So maybe I've got 2 steel balls, like with a Newton's cradle. Maybe I've got rubber, and notice clay is 0, right? So it just says clay is just going to absorb all that energy. So if we know some of these things already, or at least approximately, I should be able to take 2 known materials and put them together and see if I can get 0.9 out of it. Or I could take a material that I don't know and find its coefficient of restitution by using the same procedure. So you could use known materials to predict, compare results. Galileo also showed the oscillation depends on the length. But here, it doesn't depend on length nor mass. And I was like, well, so does it? Does the shape matter? Does the length of the pendulum matter? We have to find out. So that's something we could test. I also thought of a question of maybe how many times does it rebound before falling below a specific angle? This is maybe just my test writing brain, thinking of things I could do to make things more complicated for the sake of it. But the last one I think is probably the most interesting. And that is it possible to determine and validate which form of energy is dominant? I'm sorry, energy loss, right? Is it the drag force that dominates the energy loss? Is it heat? It's probably not sound. Maybe. I don't know. But that's the whole idea of physics, right? I should be able to measure that. So, yeah, I don't even have a questions slide. But yeah, anybody have any questions? Hopefully it wasn't too, yeah, go ahead.
Do you think that temperature would also maybe change this coefficient?
Well, one thing I forgot to mention, and I don't know why it flipped on me. When I mentioned heat, right, there might be, like I could get a nice thermal camera. Mm-hmm. I could measure the collision, do it like orthogonally right there on the plane. But technically, there's also going to be energy that's propagated inside the material that I wouldn't be able to measure. Mm-hmm. So, like the material itself would heat up, not just a heat signature that's coming out of the surface. Because the only thing I would measure is the heat on the surface, not the heat within the material. So yeah, I definitely think temperature would have something to do with that, if that's kind of what you're asking.
Yeah.
But you mean like temperature of like the ambient temperature in the room?
Yeah, like if it's, 1,000 degrees in there,
right? Or it being super cold.
Or, yeah.
Right. Yeah, I don't know. That's a good point. Definitely something you could test. And I think that's the whole point of my talk is that, yeah, okay, I can solve the dynamics problem. That's fun. And for those of you who are in dynamics, I told you guys this is going to be on your final. There's going to be something like it, very much like it. So hopefully you enjoyed it a little bit. But yeah, I think it's just all about being able to experiment and test this stuff. So hopefully, based on my last 2 talks, this is something a little bit more concrete and practical. Yeah.
Did you look at any examples to see if that formula still applied to
No, I didn't do anything. This is basically a collinear collision, not an oblique collision. Because there would probably be some geometrical proportion that comes into play with that. Well, the other thing I thought about is the force in the same direction as displacement there? Because in the case of doing work, it's FD or F dot D, but FD cosine theta. And I don't know necessarily if that's the same, not approach, but like if that's the same configuration that I'd have in a pendulum. So yeah, that's I think why the analogy doesn't work. It's because it's an apples and oranges type thing. They're not the same. So I just thought it was kind of fun to apply my kind of blindly like, oh, I made this thing. Let me see if it works. And then now I know why it doesn't. So I almost learn more from that than just solving the problem.
And
Yeah,
so,
any other thoughts?
so there's like a bunch of different kinds of steel. There's a bunch of different kinds
Yeah,
of
oh, yeah.
wood. So
Oh,
is
yeah.
this just like an average? Is
100%.
that
I should have put in a little squiggly tilde on those, because I mean, you got stainless steel. There's all these different carbide. I mean, you got so many different types of materials. So for me, it's like I just go find one that I would have a known value. Like I mentioned, index of refraction. I mean, they were measuring those for who knows how long. So yeah, we give you a piece of plastic, acrylic, whatever, and just go take a whole bunch of measurements of critical angles, and I can find the index of refraction. So for me, this is just kind of a way to get experimental values of coefficients of restitution for known or unknown materials. Yeah.
You asked if shape matters. What shape might change?
Yeah, so like if I go back to my picture, one thing that I thought about is like, what if I had instead of a sphere, I'm not gonna really scrub through this. What if instead of a sphere, I had like a dumbbell? I don't know why it's clicking on me. Hold on. You guys hear that too, right? I'm not crazy. All right. So instead of a sphere, what if I had like a mallet, and that mallet whacked up against the wall, right? I think what makes this nice, I mentioned earlier when I was talking about the coefficient of restitution, it's kind of like I'm treating these like particles than I am treating them like rigid bodies. I mean, I've kind of made it's the same moment of inertia. There's no mass transfer, right? Maybe if this is realistic, maybe some of this material here got stuck on that, or vice versa. And then the whole exchange of energy, the conservation momentum from the coefficient of restitution, it all changes. But my thought was, well, if this is a sphere, this is just a single point touching a single point on the wall. But if I turned it into like a sledgehammer and made it like a mallet space, well, then that might change, because not only will if it, I don't know, collides perfectly, what if the corner hits first? I mean, there's all those little nuances that come into play with not so nice assumptions. The drag force. Yeah, exactly. So if I had like a face here and this thing swings, maybe the top of the face hits first, and then there's just kind of this like sloshing effect. But I don't know. I thought as long as I can assume this is a single point, that's a single point, that'll all work. But if I start changing the shape of it, how will that affect it? That's something I'd like to look into. Yeah, I don't know if does that answer your question, or because yeah, I definitely think the shape would have something to do with it. If I increase this from a little point, I mean, I know it's a sphere, but like in terms of a drag force, if I increase the cross-sectional area at that face, then I'll increase the drag force, which could cause a bigger loss of energy.
Surface texture, right, would also
texture as well, right? If I've got a golf ball type thing, right? I think golf balls are supposed to reduce drag. So if I had something that was like really rough, then it would have a rougher surface area, so there'd be more drag on it.
Is this matter with mass?
No, and that's kind of what I thought was very interesting, was that in the problem statement, you know, the pendulum consists of a 15 kilogram solid ball and a 6 kilogram rod. I'm like, I don't care how big it is. I don't care what its mass is. I don't care how long it is, apparently, which that's also interesting to me.
So the same line weight distribution.
Right, and unless somehow I exchanged mass in this collision, that would be or I deformed this. Like if this is a rod and I slammed it and the rod bent, then I'm in trouble. But maybe we can measure that too. Deformations is another one, but I don't know how you measure deformation energy. I haven't done that. I haven't done strength materials in a cool minute, but I'm sure it's possible.
So the last talk was on quantum mechanics, right? So I'm wondering, have you thought about like maybe is there some like quantum phenomena or
Not
anything that's like
happening here? This
Albert,
I think, if anything, I was going to joke at the beginning because I thought, well, as much as I enjoyed the last talk, hopefully this is something that anybody can pick up on and have some concrete, tangible understanding of a classical system. So I did not even venture into that realm. Maybe another time, though.
Yeah.
But I mean, I'm sure there's some type of collision work in quantum that you could relate it to. Maybe. I'm sure. And I've made lots of assumptions that have stacked on top of each other. I think I had like 7 of them. So, yeah. Any other thoughts?
So in this example, you have like a string, a rod attached to the ball.
Yeah.
So this is more like a physical pendulum, which is not the
Right.
same as a ball that is attached.
Like
to
on a
string.
Newton's cradle with it's just a string. Yeah, but I think
So does the
it
rod
could be the same thing. Because if I don't really care how massive this is or its shape or size, assume it's a string if you want. As long as that string doesn't, wiggle. As long as it just stays tight in a state of tension. Because I think realistically, if I were to do this with a string, right, and it comes down and it bounces, there might be some stretching of that string that might contribute to energy that's lost, and I don't know how I'd measure that. So if I were going to, if I had time, I was going to bring one and build it. Make this, get like a bearing, take a bearing, you could 3D print this whole thing. And then have a little thing that I just attach different materials to. Take a steel wall or whatever material you want and just clang them together and get a whole bunch of measurements. Just take a whole bunch of data. So this, to me, is probably one of the most experimental things I've done. I'm very much, let me just think about the math and then talk about it. So hopefully this feels a little bit more concrete than my last two talks about kind of like philosophy and then everything is a ratio, which I'm kind of still piggybacking off that idea that everything is a ratio and all depends on geometry. So let me just get to the end here so I can recap I can recap that final statement. I didn't have that many slides, did I? Come on, let's transition in. There we go. All right. So yeah, for me, this is all of it. It's putting all those ideas together in one. So yeah, any other thoughts or questions, comments?
So what would be like? Let's say you constructed this for like PSC2, right?
Yeah, it could be a lab experiment.
It'd be PSC1, right?
Yeah, PSC1.
Yeah. So how would you set up the experiment? Would you have like different types of materials, and then you're measuring the coefficients,
well, I gotta
or
make
would
sure
you?
I'm only really changing one variable at a time. So I could do different heights, different angles, starting angles. I could change the material. But what I would probably just start with, if I just do one trial, is I would say, let me measure the heights and speeds that are out, measure the output angle, and compare them to these two. And then I would take all the data from the energy loss stuff, the heat, the sound, the drag force, because if I know the speed, of course, this is the speed before impact, speed right after impact. If I average them, maybe the best way to do it, then that would be the drag force speed, because it's going to go from basically 0 at rest to its max speed, and then from its max speed after the collision to its 0 rest speed. So I could just average those and plug them into the drag forces, get the work that's done by drag, find the work that's done by the work that's the energy that's lost due to heat and sound, and then just kind of add those up and see if they agree with what the non-conservative work would be, which is just the inefficiency. See if they do a little energy audit, see if anybody's laundering any energy anywhere. But yeah, I think it would be a great physics experiment, like even in a lab setting. But you could take that, you could permute all the different materials. You could find unknown material. Like I think what I would do first is say, let's make sure this works for known materials. And then if it's to reasonable approximation, and including the energy audit, then what if we talk about materials that we don't know about? I could find stuff about those, so long as these seem to hold up for things that we do know.
Yeah, because I'm just thinking, like, there's so many different compounds you could test.
And the other thing about this coefficient is, and I tried to say it earlier, I hope I said it the right way, is it's not just the material property itself, it's the interaction of two materials. So if I have like wood and metal, it's going to have a different coefficient than wood on wood or steel on steel.
Yeah.
So you could have arguably an endless number of combinations of coefficients of restitution. Yeah, anybody else?
I think I've seen a physics lab experiment right up where they just dropped super balls and measured how high they
From just straight from the ground, yeah.
Straight from the ground,
Yeah.
of various kinds, and then measure the two heights.
Yep.
Coefficients of
Yeah,
restitution.
and you'd probably have less energy loss due to friction of the axle, drag force. I mean, you're still going to have some drag, but yeah, you could do the same thing with that.
Yeah. It used to be in the demo room. They rubber balls you could drop, and one of them just sit there and just.
Oh yeah, like mud.
Yeah. But they look identical.
Oh really?
Yeah, they look like little black.
Huh.
Balls.
Maybe we'll have to look around and see if they're
I
still
don't
back
know if
there.
they're still there.
Yeah. Huh. I'll have to keep an eye out for them.
But yeah, you could. It'd be a good.
Or I could even take them and attach them to a pendulum and then put one here and then have the other one hit it. I don't know. Yeah.
I'm wondering, like, how would you? So, you know, if you have this thing and it bounces back, right? How do you easily measure how much it bounces back? Like, I mean,
The angle, all I do is just put a protractor upside down
mhm.
and just take my phone, put it in slow motion, drop it from 90, let it rebound, and then see right where it comes to a stop and then begins to fall again.
Okay, yeah, that makes sense.
Now you could do the same thing to get the angular speed, just how many frames did it take,
Yeah.
how many frames per second. Same thing with linear velocity. This one I think would be harder because I could measure angle and angular speed with the same device. But height, that's easy, just get you a ruler, right? But the linear translational speed, that might be the hardest one because you'd have to have it literally right as soon as it leaves and right before it hits. So you'd have to like really, really zoom in, you know what I mean, in a spatial sense to figure out the actual maximum speed before and after impact. So I think these three, that's why I said three simple ways. These three, this one's not so simple, at least not to my imagination.
Yeah, I think Vernier sells a rotational.
Do they?
Yeah.
Yeah, you can get the rotational speed. It's like an encoder, probably.
Yeah.
Yeah.
And it can get position or it can get velocity. So,
Yeah. And what's nice though is if I can get my angular speed and I know the length of the arm, I can find linear speed. But I'm just talking in a sense of measurement, comparing the two. Yeah.
I think it gives angle and rotation.
Yeah.
I'd have to look.
Yeah. No, I bet they do. Just have like a little rotary encoder and then it goes to the little Vernier thing. Yeah.
Nothing jazz up here.
Maybe we could get some good funding for it. We're buying the good stuff from Vernier. Yeah. Yes. Yeah, that's the Foucault pendulum. And that's kind of a different thing from here. But in the same sense of energy loss, you know there's a little magnet down there at the bottom. If you've seen it, you might not have. If you walk by it, there's a little magnet at the bottom. So have you ever seen somebody pushing their kid on a swing, right? If you swing on a swing due to drag forces and also gravity, but you're going to come to a stop eventually. So this Foucault pendulum out here precesses, so it kind of like does this type thing every so often. But the magnet down there is so that the energy that's lost, or would be, the reason I think too, if I go back to this Galileo's square root of G over L, it depends on the length. So that's why that thing's like 30 something feet tall, is to minimize the amount of energy loss, but there's still going to be some. So that little magnet down there is just supposed to give it a little kick, like you're pushing a kid on a swing, so it never runs out of juice. Sorry, I put a transition on here, and I don't do PowerPoints, so bear with me, and I'll get back to this Galileo's square root. Wait.
But it's a good point because you've ignored the rotation of the Earth.
That is another assumption. Yes, there is none of that. It's fixed to an axle, so it ain't gonna rotate. Let me just scroll through here because I think I went past it earlier.
Oh yeah, it's engineering.
Yeah, approximately pi is 3. Let's see. Yeah, these are all approximations, by the way.
Well, it could be on a swivel up there.
Up over there?
Yeah.
Oh yeah, have it be like on a pivot.
Yeah.
Where is my? I'm missing it. I know it's here somewhere. Bum bum bum. Sorry, I just want to find it because I'm in my brain. I know it exists. Where are you? Yeah, right here. The frequency is square root of G over L. So there's something to do with the length of the pendulum, which I think Dr. Wilson, correct me if I'm wrong, but that's why that thing is so long. It's like 38 feet tall or something like that. Because if I had a pendulum that was like 6 feet long, the oscillation would. It's about small angle. So the longer the length, the bigger the angle is the same, but the wider the deflection at the end is going to be. So if I had a really, really short length, the precession width would not be very interesting. That's why they've got that giant pit for it, so it can swing back and forth by some reasonable distance. Yeah, does that answer your question? Yeah, this it's related, but they're not quite the same thing. That's more like a free flowing pendulum. This is more of a I'm actually trying to see how much energy is lost, whereas that we're trying to keep it going and pump the energy back in. Just keep swinging. So yeah.
So if you knew how much energy, right? And I wonder if you think you could have like a strong enough magnet that's like pushing the energy sort of back into it, right? And if it could just perpetually.
Oh, in this case.
Yeah.
Yeah, like almost have something where like there's a magnet on the back of it, and then like a magnet at the ceiling.
Yeah.
And like as it rebounds, it just kind of like maybe it's up here and it rebounds with like 0.9. Let's say it's steel, and it just keeps pushing it back down like the repulsive force.
Well, I was thinking like on the
down
the
here.
wall. Yeah.
Oh, okay. Yeah. I mean, I think what's cool about it is there's a lot of ways you can modify it, and it all came from this simple problem from my dynamics textbook. Yeah, I'm weird like that. Yeah. Anybody else have any thoughts?
So could this be related to the refractive index somehow, like from light bouncing off
I don't know if it.
surface?
I mean, mathematically, I'm not sure, but conceptually, in a kind of a qualitative sense, I think it is a material ratio. Right? The index of refraction is the speed of the light over the speed in the index, or the speed in that whatever material it is. So in a way, you're kind of getting the inverse, which is the output speed or the input speed here. Versus there, the numerator is c, and the denominator is the velocity of the medium, which is always slower than c, or c or less. So you're going to get an index of like 1 to 1.45 or something. Whereas this, you're actually looking at the other regime where you're in between 0 and 1. So you might be able to flip a ratio around or something, and maybe you get it to relate somehow. But at least qualitatively, I think they have to do with a material interaction of some kind. I think to that extent, yeah, they're kind of related.
Anyways,
Anybody else?
If nobody
Well,
has,
I think it's 3:52, so I want to make sure we get out of here. For anybody who's going to go to the seminar,
can we
thanks
give
for everybody coming?
a round of applause? Real quick?
Thanks, y'all.